Hello everyone, this is Robert Guderian, and we will continue our adventure with Numpy. And here's a quick reminder about how we're going to make some random data. We can choose a single point, or we can create an array of size 10 with some random data. We will use that today. Here's a little reminder of what it looks like. 3, 2, 1, go. So array of mathematics. This is where Numpy gets awesome. You can do math on our arrays, which we can view as matrices. And all of our normal math, plus, minus, multiply, floor divide, modulus, power, and including our comparison operators of less than, greater than, equal to, less than, or all of them. They're all there. And it's done element by element. So we have to see what this looks like for that to make some good sense. So let's say that we have an array of 1, 3, 5, 42, and 10, 2, 3, 1. Put commas between all those. So when I say element by element, I mean we're basically going to be looking down these columns. And when I say add, we can imagine a world where we can draw it like that, and we will add these together one by one to make a new array, and there will be a third array now in existence. That is the sum of each element going down the columns. The same thing works and is true with Booleans. Doesn't really matter what my data is. 5, 3, 1, 0. Good. I could say less than or greater than here, and it will do this operation down the columns again, and it will provide me an array of Booleans as output. So is 5 greater than 1? Yes. Is 3 greater than 3? Tricky. False. Is 1 greater than 5? No. 42 greater than 0? No. Okay, neat. So an interesting thing, I mentioned this last time, is that Booleans are actually stored as a bit. 0 is false, 1 is true. We're going to use that feature later. Keep that in mind. This is called SIMD, single instruction multiple data. Fancy processors can actually do this to multiplex data. This is what your video cards will be doing, which is very, very cool, but an interesting thing. For us, it's syntactic sugar, meaning that we just have beautiful syntax that'll do lots for us, and that's nice. Pretty much what you saw. Well, let's actually code it up. Import numpy as np. A1 is equal to, I'm going to use a range. I feel like it's a little bit tidier. I'm going to restart my kernel to get some fresh stuff here. And np dot a range from 0 to 10, and I'm going to give, well, that's it. We'll have 10 of those. A2 is np.a range from 100 to 110. So both of those are 10 long. And then I will say A3 is equal to A2 minus A1. So what is 0 minus 0? 0. So 100 minus 0 is 100. 101 minus 1 is 1. 102 minus 2 is 2. So A3 should be all 100s. Let's find out. It's A3 with a lowercase a. You don't have to spell it right. You do have to spell it consistently. Boom. Yay. Multiplying, kind of the same jam with a star, and that will happily multiply for us. And it's actually pretty quick. The slowest thing is actually Python starting in this case. And it, if we do our conditionals or comparison operators, it will indeed give us a set of all false. Yes, indeed, 0 is less. 100 is not less than 0. That is, in fact, true. So that's great. What more can we do? Oh yeah, let's break this, because somebody's going to break it. So what happens if these are not the same size? 109. It will complain saying that they're not the same size. Operands could not be broadcast together with shapes 9, 10. And that is because one of them is 9 long, one of them is 10 long. It cannot do element by element because they don't match up. So it'll say, no, I can't do that. Go away. Try again. Do not pass code. Do not collect $200, etc. So it's not the best error message, but you've seen it, and you know that the size thing is really what you're looking at there. There's beautiful functions. We've probably made you do these by hand. It's not because we're cruel. It's because it's important that you know how to do it by hand. But Numpy can do it for you. If you want the sum of an array, you just can call .sum on it. Product will multiply them all together. Mean is the average. STD is standard deviation. I don't know why they'd choose to do it that way, but that's okay. Let's say print the sum of A1, and that'll actually work too. This is the built-in function for Python, but that'll be Python actually iterating over the whole thing. It's gonna be kind of slow. What we want is .sum, and then it will sum it up for us. That will actually run faster because it's running with NumPy, so that it will actually work differently, which is fascinating. .mean, same thing. Standard deviation, the same thing. Beautiful functions. There is more here that we can play with. This was the closest anchor tag I could get. If I scroll down, it'll show me all the functions. There we go. Some of these won't make sense to us. It's a good idea to just read these over to know what's available. Cumulative set of sum, cumulative product. Interesting, I guess. Fill. Think about np.0, which will give us a bunch of zeros, and np.1, which give us a bunch of ones. We could recreate that by saying np.0 and then fill with ones, and then the whole thing will just be ones, which is nice. And reshape is interesting. It'll actually let you change the shape of it, which is crazy. And most of these we won't use, but the ones we'll use the most are highlighted in the slide. So that's nice. There is even more functions available to us. These ones are called on the library. So np.abs is the absolute value, median, mean, std for standard deviation. Why would they have both? Sometimes you don't have an NumPy array and you want to call these functions. You can actually call these functions on the list, which is cool. And some people just have a different flavor. People who have learned C, like calling functions like this versus doing the object-oriented array.sum. So whatever your flavor is, it's fine. Know how to read both, know how to do one, know what your flavor is. And there's a few more things here that we can do too. This one actually has variants. I didn't actually notice that in the NumPy array, but it's probably there. I just didn't notice it. Woo! Copy an array. Oh, let's do one more mathematical thing. We can also add with scalars. So if we have a A1 plus 100 plus 200, it'll add it to each and every element. This is what happens in linear algebra 2. If you have a scalar, you can just add it to every single item inside of your matrix. It works. It's handy. But now for the tricky stuff. Do you remember Pass's reference? I'm sure you loved Pass's reference and it made perfect sense at that time. Let's look at it again. So if we have a bunch of functions, we have a stack, and that's where everything runs. Our primitives live there, and then we're going to have two arrays, 1, 2, 3, and 3, 2, 1. We're going to have a couple of variables. We're going to have A and B. And since these are objects, all we actually have is a reference. Okay, that's fine. And this will be, these pointers will be shared throughout the whole. If we pass B into a function, then we would be passing as reference because all of our object data is living on the heap. Now, what if I do this? Well, all we're going to do is copy the pointer. What if I do this? C0 is equal to 42. Well, I'm going to look at my C pointer, and I'm going to overwrite element 0 with 42. Now what happens if I print A? Well, A now has changed because they're pointing to the same object. That doesn't feel good. Let's take a look at what that looks like. So we're going to give some visual space here. And we're going to say A4, I guess, is equal to np.arange of 10. This really doesn't matter. Then we're going to say A5 is equal to A4. Okay. A5, which is this, we happen to know is just pointing to the same data space as A4. Sub 0 is equal to 42 because nerd things, and print A4. If this indeed is working the way that I am telling you, we'll see a 42 when we print out line 17. 42. That is not nice. Even if we look up here in our variable explorer here, I can say A5 at spot 1 is equal to 1, 1, 1, 1, 1. And we'll see it change in both of these spots. So I'm going to switch to this view. Both of these will change because they're both pointing to the same object. Ick. Don't like that. All right, so that's probably not what we want, unless that's exactly what we want, which is maybe the case, maybe not. What if I do this? .copy. .copy will do something called a deep copy. It will create a brand new array with the same data, which is actually an expensive operation. If whatever space is taking up, now we have to take up double the space because I have two identical copies. Then when I run the second one, 42 will not exist because when I'm changing A5 here, it's changing A5, not A4. And that is because, if we jump over to this, when I call copy, I'm going to draw a new A. We're going to point into here, to some data. 1, 2, doesn't have to be a big one. If I say AC is equal to A.copy, C, I'm pointing into here, pointing at brand new data, and that's probably what we actually want. Now, when I'm changing C, it's totally destroying the copy, not the original. So that is an important thing to remember. These are objects. We need to treat them like objects. Pointers matter. Woo! So one example, we're going to generate a random list of data and do some work with them. Like I said, we'd do that at the beginning. We've already mentioned this. So the idea with NumPy simulations is that we're going to do it differently than before. What we're going to do, because we have this array that we can create, and we can create it with a whole bunch of data in it, we're going to create the whole data set at the beginning. Then we'll use array operations to do whatever we want, and then we'll process that data at the end. I'm going to come back to this one. I'll do this one in a video beside, because I'm really excited about this. We're going to go back to throwing dice. How often will a D12 be a D20? And we want to get the percentage of times that happened. Well, we've already done this. We already have that code. But let's create a new file and try this with NumPy and see what it would look like. And remember that we're going to do it differently. And that's really distracting, so we're going to put that away. Import NumPy as NP. So we have our D20 is equal to np.random.randint. And we're going to have a trials sets. I'm not going to call it trials. I might have to change that for my next thing, and that's okay. It doesn't really matter. 100. So we want a dice that is a D20. So that is from 1 to 20, including 20. So that means, because of how randint works, we have to go up to 1 to 21, because that'll go up to and not including 21. That doesn't feel nice, but we can deal with it. Size. Our size is trial size. And we're going to run this. I'm going to reset my kernel. Yes, I would love to say this. Dice num np. Dice and b and p. Sure, that sounds great. I'm going to reset my kernel. which you can't actually see, but that's okay. And then I want to have my D12 is equal to pretty much the same thing, np.random.randint 1 to 13 ick, and then trials amounts of that. Neat. I love it. Now we want to also have the idea of a modifier to see how many times we win. As you remember from last time, D12 plus something, and will we beat the other thing? We're going to do, we want this to do this apples to apples. So our data set exists, and we're never going to change our data set. For modifier in range, we're going to start at 0 and go up to 6, I guess 7. And then we will do the math. Well, let's maybe do it just once to see if we can do this, and then we'll add the modifier. So I want to see if D20 beat the D12, and this is all random data. So let's actually get a little sniff of our data. Okay, bunch of numbers, bunch of numbers. How would we check if D12 is greater than D20? D12 win is equal to, is the D12 roll better than the D20 roll? I'll give us a third array of Booleans. Now, I want the percentage. Well, all I have to do is get the mean. Now, this is wacky and fun. So remember that Booleans are 1s or 0. So true, true, false, true would be 1, 1, 0, 1. And if I could create the average, get the sum of this, that would be the number of wins. And I could divide that by the length. But that's the exact same thing as calling average. You can prove that to yourself. I'm fine if you just do it this way. I don't really care. I'm just going to call mean on it. Print D12 win dot mean. And that will give us a percentage, and I'll be as between 0 and 1. So only 30% of the time did that happen. I could multiply this by 100 if I want to not be an ape about this. 100 has, there it is. There we go. Neat. Now, further, let's do this in a for loop. Changing that modifier. Tab this in. Tab this in. I want to do this plus mod. And we know that's a scalar. That will add whatever our modifier is, the first 0 and then 1, to the all of D12. And then order of operations will run my comparison afterwards, probably. Well, we can force it. I'm not actually certain that's the case. And I don't have to be certain. I can just be smart and tell it what I want. I need a more interesting thing to print here. So I'm going to say D12 plus something. It wins something percent of the time. And I'm going to format this to a point. Guess what? 0.2. I'm not sure you're shocked by that. Percent of the time. If the time. The time. And dot format. We're going to pass it in flexible space. We're going to pass in the modifier. And then we're going to pass in that. Generally, you won't have to do prints like this. I have to so you can actually see everything. If I run this, it gives me all the sets. Is this faster? I wanted to prove to you if this was faster. So let's do it. Copy this, and I have dice v2. And I have my original dice program, which had runs. I'll have to change trials to runs. This is unmodified. My control var is up top. I put a comment there. I added some timing stuff down here to see how long it takes to run all of these. And it looks like we go from 0 to 10. So we'll put our new stuff here. Paste. This is now runs. This is now runs. And we need to change this to 10 to compare properly, 7 out of 10, with our other version. So this is the new version. I copied and pasted that. Can you tell? I'm just going to compare legitimately old version and new version with running 1,000 trials. Bang. NP is not defined. That is true. Import numpy. Numpy as NP. BP. Not Boston Pizza and or British Petroleum. 0. So these are actually interesting numbers. 0.1 is second and 0. Let's increase this. Runs. Well, I might have to pause the video. Have a sip of coffee. Yeah, now I'm dumb. And that's okay. I can pause you. I'll do the thing. Watch this. Whew. All right, I actually changed my code. After going for a nice snack and not having the first one completed yet, I decided this would be a bad idea. So I changed it to what looks like 100,000. If I run this, it's funny. You can see the old version of the experiments kind of scroll through. And then the new version of the experiments take 0.7 seconds. So interestingly enough, I'm going to just comment out all this stuff. I think I can highlight and press Control 1. Some student showed me that once. Oh, Command 1. Hey, cool. I'm going to actually increase this until it actually does take some amount of time. Let's add 2 zeros. So this is just the new version. Time is not... I imported time right there. Shame on me. That's why we don't do that. It still runs at a reasonable speed. How many zeros would I have to add to go as slow as the old version? Well, it's going to take 10 times longer, isn't it? Interesting. I wonder if you have enough zeros, if it starts swapping. We can talk about what that means. Oh, first one just finished. Still much faster. Overall, what does dot mean on Booleans? You're summing up all of the ones, dividing by the population. That gives you a percentage. That's cool. This works for sum too. Very important. And yeah, this is way faster. Overall, this summary here is that with experienced NumPy, we're creating our data set up front, which feels different. So we're going to have to take a step back and actually look at what we want to accomplish before we can program it. It's really a good idea to try doing this on paper first and say, okay, this is what I want. I can program that. And my experiment was what, 6 lines of code versus my 50 for the other one. We can be very expressive with NumPy, and that's what makes it hard. This working with NumPy, it's very smart to sit down, do all the work before you start programming. Otherwise, it's going to be really hard. And do it piece by piece. You saw that I wanted to jump straight into the for loop. That's a bad idea. Try just getting the simple case done, and then try repeating that with the for loop. Put that into a function. Try repeating that. Break down the pieces. Have a good day.